Hydrolysis of an ester.
Acid catalyzed hydrolysis of an ester. This mechanism is applicable for esters where the R group is either a primary alkyl group or secondary alkyl group. Now, when you add an acid to the reaction, the first thing that's going to happen is that the acid will protonate the atom in the reactant which has the greatest electron density. Here in ester, there are two oxygens, and between these two, this is the oxygen that is going to get protonated. And the resonance contributor is also going to tell us that this is the oxygen which has the greatest electron density, and therefore this is the one that's going to get protonated. Let's draw the resonance contributor for this ester. So these electrons from the oxygen is going to go hop in here to form the double bond, and the double bond here is going to break, and it's going to move on to this oxygen. So when you draw the resonance contributor, it's going to look like this. And as you can see from the structure, this is the oxygen. It has more electrons around it, and therefore when it reacts with the acid, this oxygen is going to get protonated. Okay, now let's do the mechanism. So the first thing that's going to happen is this oxygen with more electron density is going to get protonated. So the electrons from this oxygen is going to go abstract this hydrogen, and it's going to thrust the leaving group out so as to form the protonated ester. Now in the next step, it's going to react with water, right? So water is going to act as a nucleophile, and it's going to make a nucleophilic attack on this carbon, thrusting these electrons onto oxygen, thereby producing a tetrahedral intermediate. Here is the first tetrahedral intermediate that is created, and I'm going to name this as 1. Now in the next step, a base can come in and abstract this hydrogen to form another tetrahedral intermediate. Now the excess acid in the reaction mixture can also protonate this OH3 so as to give us one more tetrahedral intermediate. Let's also draw the structure for the other tetrahedral intermediate that will be formed. Here is the structure for the other tetrahedral intermediate, and we are going to name this as 3. While tetrahedral intermediate 1 and 3 are protonated intermediates, tetrahedral 2 is neutral. So this is neutral, whereas these are protonated.
This neutral tetrahedral intermediate can get reprotonated at OH to give tetrahedral 1 intermediate,
or it can get protonated at OCH3 to give us the tetrahedral intermediate 3. Now when tetrahedral intermediate 1 collapses, it's going to have water as the leaving group, and it will give us back the ester. But when tetrahedral 3 intermediate collapses, it's going to have the alcohol as the leaving group, in which case it is going to give us the carboxylic acid that we want.
The relative amounts of these 3 tetrahedral intermediates is going to depend on 2 things. One is the pH of the solution, and the other one is the pK of these tetrahedral intermediates. So first one is the pH, and the second one is the pK of these tetrahedral intermediates.
Now let's write the compound that we'll be getting as this tetrahedral intermediate collapses. So the electrons from oxygen is going to thrust back in to form the double bond. And since this is going to be a good leaving group, the alcohol is going to be a good leaving group, it's going to leave from the system, giving us back the protonated carboxylic acid. Here are the products obtained. We have the protonated carboxylic acid and the alcohol. Now again, a base comes and abstracts this hydrogen to give us the carboxylic acid that we want. Now one thing that we have to keep in mind here is both of these intermediates, tetrahedral 1 and as well as tetrahedral 3, are more likely to collapse, right? So you will get a mixture of carboxylic acid and as well as the ester. But how can you drive the reaction in the forward direction so as to get carboxylic acid? One thing that you can do here is you can periodically remove the alcohol that has been obtained. If the alcohol is going to have a lower boiling point, you can easily distill that off
so as to prevent the backward reaction.
Or what you can do is you can use excess water so as to drive the reaction in the forward direction. Both of these two things is going to make the reaction to go in the forward direction, thereby increasing the amount of carboxylic acid.
This should have the arrows here.
The trans-esterification reaction also goes through pretty much the same mechanism. Here again, we have to use excess of alcohol to make the reaction to go in the forward direction. The use of acid catalyst is going to increase the rate of the hydrolysis of ester. Now the acid is going to serve two purposes. The first one is to protonate the carbon and oxygen. If the carbon oxygen is going to get protonated, it's going to increase the susceptibility of the carbonyl carbon towards nucleophilic addition reaction. Let's compare the structures of the protonated ester and non-protonated ester. The protonated ester is going to have a more electron deficient carbon because this positively charged oxygen is going to withdraw more electrons towards it. Thereby, the nucleophile can go and attack this carbon very easily compared to this one. The second thing is that the protonation is going to make the leaving group a better leaving group. The acid that you add is going to increase the rate of collapse of the tetrahedral intermediate by decreasing the basicity of the leaving group. So let's consider these two structures. So here the leaving group is not protonated, but here it is protonated. So between these two, obviously this is the weakest base and therefore this is going to be the best leaving group. So the collapse of this tetrahedral intermediate will be much easier than this one. The hydrolysis of an ester with a tertiary alkyl group is also going to give us pretty much the same product, which is basically a carboxylic acid and an alcohol. So no matter what the alkyl group is present, an ester that undergoes hydrolysis in the presence of an acid is going to give us carboxylic acid and an alcohol. But the mechanism here is going to be completely different. It's going to go through an SN1 mechanism. The first step is exactly the same here as well, where the oxygen with more electron density is going to go grab this hydrogen from the acid to give the protonated ester. Let's write down the structure for protonated ester. And in the next step, this part right here is going to leave from the system, giving us a carbocation. This is where the actual SN1 reaction takes place. This highlighted part is your leaving group, and that's going to get eliminated as carboxylic acid. So this bond is going to break, and the pi bond is going to break, and those electrons are going to move on to oxygen to neutralize that positive charge. By this, we'll be getting carboxylic acid and a tertiary carbocation. Now in the next step, the second step of the SN1 reaction takes place, which is basically reaction with a nucleophile. Here water is the nucleophile which goes and attacks this carbocation. And this is basically a protonated alcohol which will be deprotonated using the base. And it will finally give us the alcohol that we want. Okay, so the two products that are obtained here are the carboxylic acid and the alcohol. The rate of hydrolysis of an ester can be increased by hydroxide ion. Like the acid catalyst, the hydroxide ion is also going to increase the rate of the two steps, which is the formation of tetrahedral intermediate and the collapse of the tetrahedral intermediate. Now let's take a look into this mechanism. First, to begin with, the hydroxide ion is going to go make a nucleophilic attack on the electrophilic carbon. So this is going to go and attack here, thrust these electrons onto oxygen. That's going to give us a tetrahedral intermediate. So here is the tetrahedral intermediate that is obtained. Here, both of these groups, the OH group and the OCH3 group, have got pretty much the same propensity to leave as these electrons are going to come in, right? Because both of them have about the same basicity. Both of these groups have about the same basicity. When you eliminate the OH group, it's going to give us an ester. When you eliminate the OCH3, it's going to give us the carboxylic acid. Now the product here will not be a carboxylic acid because this is definitely going to exist in the unprotonated form. Because OCH3 is more basic, so it will go and try to grab this hydrogen so as to form the alcohol, and the carboxylic acid will exist as carboxylate ion. We have said earlier that the hydroxide ion increases the rate of formation of the tetrahedral intermediate. This is because the hydroxide ion is a better nucleophile than water. Right? So in the acid catalyzed hydrolysis of ester, we only use water as a nucleophile. But here we use hydroxide ion, which is a better nucleophile. And obviously with a better nucleophile, the tetrahedral intermediate will be formed faster. When we go on to the second point, how does the hydroxide ion increase the rate of collapse of the tetrahedral intermediate? For this, we have to look into the transition states of the two tetrahedral intermediates that are obtained. Now, here is one tetrahedral intermediate. The other tetrahedral intermediate is where this O minus is going to get protonated, right? So here are the transition states for the negatively charged tetrahedral intermediate, and this is neutrally charged tetrahedral intermediate. For this tetrahedral intermediate, as the OCH3 is going to leave, this oxygen is going to develop a negative charge on it. But for the protonated one, as the OCH3 leaves, this oxygen is going to have a partial positive charge on it. So therefore, this is going to be the one that's more stable because you cannot expect to have a positive charge on the electronegative atom, and this is less stable. So for this reason, we can say that the hydroxide ion is going to increase the rate of collapse of the tetrahedral intermediate, wherein it forms the most stable transition state. The main difference between acid catalyzed and hydroxide ion promoted hydrolysis of an ester is the acid catalyzed reaction is a reversible reaction. So this reaction right here is a reversible reaction, whereas the hydroxide ion promoted reaction is an irreversible reaction. So this particular reaction is cannot be called as base catalyzed reaction. Instead, it is called as hydroxide ion promoted hydrolysis because the hydroxide ion is getting used up in the reaction. If it's going to be a catalyst, then you will be able to recover the catalyst at the end of the reaction. But here, the hydroxide ion is consumed in the reaction. As the hydroxide ion acts as a nucleophile, it is being consumed in the reaction. So that is one of the difference in the between the acid catalyzed and hydroxide ion promoted hydrolysis. And the second thing is that the hydroxide ion only promotes the hydrolysis reaction. It does not promote the transesterification reaction or the aminolysis reaction. Because in transesterification, where one ester is converted into another ester, you have to use another nucleophile that is different from the hydroxide ion. Say, for example, if this methyl ester needed to be converted into an ethyl ester, then probably you might want to use the ethoxide ion. Right, so that is going to be the nucleophile and not the hydroxide nucleophile itself, right? And also in the case of aminolysis, you have to use the amine as the nucleophile. So the hydroxide ion can only be used for the hydrolysis of an ester and not for transesterification or aminolysis, where the hydroxide ion does not take part as a nucleophile.